So, yeah, we are adding about 2,020 people to the world every day, about 80 million per year, meaning more mouths to feed. And not only that, more people eat more fish. And because people go off red meat for the health benefits into poultry and onto seafood. And to provide for that demand, we have been very efficiently in emptying our oceans. As you know, fish is the last, or fish are the last hunt and gather kind of a practice. You don't go to the wild to fish, to hunt for your poultry or cattle, but you do it for fish. And this led to the tragedy of the ocean. I mean, we all know about it, but The Economist had a few interesting cover stories a few years ago. And later on, they came with a solution, which is the Blue Revolution, the promise of fish farming, or aquaculture. Aquaculture, which is the farming of commercially important aquatic marine organisms in captivity. As a result of that, more people eat more fish and emptying the ocean. We see this widening, or we have been witnessing over the last years, the widening gap between the demand, the ever-increasing demand of seafood, and at best, the white line is the at best at leveling off fisheries. And this increasing gap has to be filled by aquaculture. This is a challenge for aquaculture. Responding to this challenge, aquaculture has become the fastest growing agricultural industry in the United States and globally. However, it needs to become a much more cost-effective, efficient, and mainly environmentally sustainable industry. And for that to happen, it has to overcome all kinds of hurdles, open some bottlenecks, and I'll just give you two examples of those bottlenecks. The first of which is no spawning in captivity. So when you take rockfish like this fish, and this is a tank in our basement, fish do not reproduce because of the stress associated to captivity. And you cannot start a cost-effective, efficient aquaculture industry without being able to close the entire life cycle, namely producing eggs and juveniles. I call them seeds, like any other crops in captivity. So the challenge was to close the life cycle. I'm going to tell you now in 30 seconds or 1 minute what we did over the last 25 years to solve that problem. And so we wanted to compare the entire physiology between the fish that are raised in captivity that do not spawn and those fish that are coming from the tributaries of the Chesapeake Bay, the spawning ground. Like you see this fish, huge fish, is being sampled. It is alive. It will go back to the water by an ex-graduate student of mine, Dinos Milonas, at IMET. And so he just took, you see by the tail, a blood sample from this fish. This is very good, but the bad thing is that he's carrying the syringe in his mouth, which is not a good practice. So the point is that we studied the entire reproductive cycle, you know, all the hormones and the genes that regulate reproduction in an effort to locate the level of the failure, the hormonal failure. Because of the lack of the environmental condition, there is a hormonal failure, and we ended up narrowing it down to one brain hormone that jumpstarts the entire reproductive system. We synthesize it, we produce synthesized version, very super active, super potent versions of this missing brain hormone. And as you can see here, we injected fish. You see the stripes to your upper left, the high-value sea bream to your right. You see then you see myself years ago when I had like darker hair, injecting in the field on the net pens Atlantic salmon, and even we use it for like high-value ornamental fish like the sea dragon. It's like close to being extinct from the Great Barrier Reefs, and they go for about $5,000–6,000 a piece, only to like national or state aquaria and things like that. And we made those fish spawn and solve that problem. Now here's another fish that is being fished out, bluefin tuna. There is a lot of effort to develop aquaculture and then spawning, closing the life cycle of the bluefin tuna. Obviously, we cannot inject those fish that we anesthetize for a short time. And so what do? We cannot inject them, so we shoot them. With this, we send like a free diver with a spear gun. At the tip of the spear gun, there are those small hormonal implants, the delivery system that go into the fish. The green thing is just a tag to tell us that those fish were tagged. By the way, those delivery systems, those hormones, they disappear, they biodegrade in a couple of days. The fish start to spawn, and then it continues. And here you can see some of these big bluefin tuna. Those are, by the way, about 400 or 500 pound fish. And you see that a couple of them are tagged. They got the hormone. A few days later, we have the eggs, very tiny eggs under the microscope. They're about 1 millimeter in diameter. And then and then we produce for the first time in North America juvenile bluefin tuna, and you can see the very tiny ones in our tanks at the Columbus Center, at the basement. Those are larvae bluefin tuna. To the left, you see the beautiful small fry or juvenile, and then those are like hand-fanned bluefin tuna in Baltimore, in the Columbus Center for the first time ever. Switching gear to the other bottleneck, which is the major one, which is aquaculture, the interaction of aquaculture and the environment. You probably heard a lot about it. The issues are chemical pollution. 95% of aquaculture, or fish farming, is done using these practices, floating net pens in the marine environment. This is in a beautiful fjord in Norway, and obviously lots of fish in those net pens, and you have chemical pollution, like runoff, feed residues and leftovers and so on. You have biological pollution, which is huge because aquaculture farmed fish have been selectively bred. They are different from the wild fish. They escape. If you grow Atlantic salmon in the Pacific Northwest, which has happened, they escape, and so you have an invasive species all of a sudden. And then disease transmission. Aquaculture is being blamed for transmitting disease from the net pens to the wild, but really the other way around is more of a problem. The fish are catching a lot of diseases from the wild, from the environment. And so we have been developing for many years on developing an alternative practice and a new generation of sustainable aquaculture, and it is land-based, fully contained, so it can be freshwater, but we're already focusing on the marine, land-based, fully contained, recirculating aquaculture. So what you can see here, those are tanks in our basement at the Columbus Center, and the water, we start with city water. We make artificial seawater simulating all the trace elements that need to go there. We can simulate now the Atlantic Ocean, the Pacific Ocean, the Gulf of Mexico, the Mediterranean, and so on to provide optimal conditions. And the water recycle again and again and again. And you see in the red circle, there is, those are like biofilters. Those are communities of microorganisms that remove the waste produced by the fish so the water can recycle. The microbes live in kind of symbiosis with the fish and remove the waste produced by the fish. And here you can see, this is one of our tanks. I don't know if anybody of you recognize this fish. Bronzino. So the European sea bass, we talked Italy a minute ago. So this is the Italian Bronzino, the French Dorade Royale. In our basement, you see how the water is pristine. It's the same water for the 10 months grow-out cycle of this fish. And here you can see some other tanks, and I'm sure you cannot recognize the fish in this tank. And this is Atlantic salmon. And this study, by the way, is funded by the Tedco Maryland Innovative Initiative, and you can see some of this Atlantic salmon. So here's the opportunity with Atlantic salmon in this country. 95% of salmon consumed in the US come from overseas at a value of about $3.4 billion annually. A huge contribution to the US trade deficit. Responding to that, now we see a wave of trying to grow fish locally. Obviously, the opportunity is there. Grow Atlantic salmon locally, but you cannot grow them in these floating net pens because of the adverse effect on the environment. And actually, they are not allowed anymore in the United States. So we have to go land-based using those technology that we are developing. And right now, as we speak, there is a $1 billion investment in land-based Atlantic salmon production in the United States, including in Maryland. And this is happening. So now we're talking larger scale. This is like in Indiana. I mean, the big benefits of those systems is that you can go, I forgot to mention it, it was on the slide earlier, but the big benefit of those systems that, I mean, they solve all the problems, right? So they have no interaction with the environment, they are disease-free, there are no escapees from these systems, and they can put anywhere. They can go to, they don't need to be by the coast. They can go into either urban, like us in Baltimore, or rural communities, and they reduce the carbon footprint. You can put them next to your market, you can put them next to your airport, and this is in Indiana. So growing salmon in huge tanks in a big warehouse, and you can see how dense packed the fish are, but the problem is, and here's the main hurdle, is to remove the waste. Because fish are eating a lot and are producing a lot of waste. One farm, like the one that is producing 5 million pounds of fish annually, will produce hundreds of tons, it will produce, hundreds of thousands of pounds or hundreds of tons daily, every day, of waste, of organic waste, of solid waste. So what do we do about it? And this was our solution, is to really simulate, again, going back to the microbes, and simulating processes that occur naturally in the ocean. And in this case, Methanogens are marine microorganisms that, as the name implies, they produce natural gas, they produce methane, and this is in the marine environment. It's combustible kind of methane and so on. So we wanted to use the same thing in our system because they are coming, those are all beneficial microbes. So we start with fish waste. You see in the small flask to your left, we start with the fish waste that this bottle was initially very, very dark, full of waste, and we use the methanogens, those microorganisms from the fish waste. They are there in the fish waste. We enrich them. You see the bottle is becoming kind of clearer, and so those are the methanogens that are converting the organic waste into methane, and then we mass culture them in this fermenter in our building. It's a microbial fermenter that is 250 liters, about 60 gallons, that takes those enriched microbes and produce many of them at high densities. And then you can see at the bottom a small canister. Then we harvest them, you'll see in a minute, and we inoculate them. These are the tanks. You see the blue tank. Next to it, there is this, we call it anaerobic digester, or the bioreactor. And the waste comes at the bottom, and the biogas goes in the top. And we, of course, collect the biogas. And there you go, right off the fish tank. You can start a Bunsen. Those are totally flammable, fuel-grade methane. And we can start a methane-driven generator and generate electricity. So all of this was done by our team and so on, and then Norway heard about our work. Norway is the largest producer of Atlantic salmon in the world, major imports from Norway into here. It's about $7-8 billion industry in Norway. You see here northern Norway, there was like a very state-of-the-art fish production operation of Atlantic salmon, producing a lot of fish and daily producing 6,000 pounds of waste daily, and they had to do something about it because the Norwegian, long story short, they changed their policy and the laws, and they cannot anymore kind of release it to the fjord, to the wild. You can see to your right the farm, and so we told the Norwegian, well, okay, send us some of your fish waste. Fish poop, basically, because we are really tailoring the microorganism to the fish of interest. And here you can see the same fermenter, and Kevin Sowers, Professor Kevin Sowers, the methanogen expert, is kind of harvesting the scaled up methanogens, microorganisms that came from the Norwegian waste. And then, in the meantime, well, the other fermenter, the other bioreactor that I showed you from our basement was about 250 liters. So again, 60 gallons. Now in Norway, it's a big industry, it's a big facility, it's 100 cubic meter or 100 times more, larger than what we have in the Columbus Center. So it's 25,000 gallon bioreactor to convert the waste into biogas. And here we are in Norway inoculating. So we are taking this canister, ship it to Norway, go there, we inoculate it, we called it inoculation date, and it started to produce biogas and so on. And the Norwegians are using it to run methane-driven generators to heat their water. They are at the very north part. They need to heat their water, and to the right they have sometimes you have too much methane, so you flame it out. You have a biogas flare to the right. And not only that, the original idea is to remove the waste, to be environmentally responsible in terms of this aquaculture system, but in the process you produce biofuel, fuel-grade energy that offset for them 10% of their energy costs. So these two technologies, these two bottlenecks that we dealt with, enabled, obviously, the industry to grow, to be environmentally responsible, to be more efficient. And this is just my last slide. It's another nice tank at IMET, at our basement. And so we think that this is kind of helping this blue revolution that was on the first slide, the Economist paper. And wanted to thank you very much for your attention.